learned some new stuff, vectors for the first time, and so let's go back and review that before we do any new stuff. Alright, here we go. Take out those notes. This would have been your problem of the day today, but since we're not together, we're going to have to do this right now. So first, I want you to find the component form of this vector. This vector up here above my head is vector v. So let's go ahead and do that right now. Let me move my microphone over so that you can hear me better. There we go. Alright, so vector v is this beautiful vector right here, and what I'm doing to put it in component form is just to make it so that the initial point right here actually is at 0, 0. This makes our lives a little bit easier with the math, so that's why we would want to do this. So basically, I'm moving it so it was here where the green line is, and now it's going to be there. In order to move that, first I need to figure out where my initial point would be, and that's -2, 4. And then my terminal point for that original green line is 1, -3. Now remember, to find component form, we're going to put our little elbows here, and a comma, and more elbows. And then after that, I'm going to start with whatever number the arrow is pointing at for the x. So the x was pointing at 1 here, so over here I'm going to start with 1 and then subtract this thing right here, the other x, which was -2. Then I'm going to go over to the y value that the arrow is pointing at. That right now is -3. So I'm going to come up here and put -3, and then I'm going to subtract whatever was here. That was 4. So my final answer in component form is 3, -7. And that's all there is to it. If you'll notice, the new line, when I took that original green one and moved it so that it started at 0, 0, the new line, it ends at 3, -7. So that's my new vector. Alright, so let's move on to the second one. We want to put this in linear combination form. Now you just told me that 3, -7 was our vector in component form. It is so easy to put it in linear combination form. You've got a 3 and a -7. The first term has an I in it, and the second term has a J. And that's it. The only difference is there's no elbows, there's no comma, and we're just making it just like an expression. That's all. Next, let's move to the magnitude. We remember that the magnitude, you can show it like this, like double absolute value bar things. Now that just means the distance. So we're going to do the distance formula. And let's go back and remember what our vector looks like. It's 3, -7. So here I'm just going to take 3 and square it, and then I'll take -7 and square it. This is the advantage of having it in component form. I don't have to do the full out distance formula. I can just square each of the values. Alright, so in here that gives me 9 and 49. Inside there that is 58. So you would agree that the square root of 58 is the magnitude or the distance of this. If you want to kind of check your answer and see if it's right, let's do the square root of 58 in the calculator. That gives me about 7.6. So if we're rounding it to 7.6, we would ask, is this line about 7.6 units long? Well, if we went down 1, 2, 3, 4, 5, 6, 7, if it went straight down to there, that would be 7 units. But then we dragged it diagonally across, which had to stretch it just a little bit, so it's going to be a little bit longer than 7, which 7.6 makes total sense. Next, I'm going to find the angle between v and the x-axis when v is in standard position. So I'm going to take this and I'm going to put it back into standard position. Remember that went from 0, 0 to 3, -7 down there. So I'm going to draw this new vector. Alright, there it is. Sorry about the color. You're going to have to deal with yellow. So that's our new vector. I want to find the angle between here and the x-axis. So just take a guesstimate. What would this angle be? Well, to me, it looks like it's around maybe 60 degrees. So we're going to look at our final answer after we get it and then assume it should be close to 60 degrees. If it's not, maybe we screwed up. Alright, so Our initial vector is 3, negative 7. This is in component form. This is this yellow one right here. Honestly, it's the same as this red one, but for our drawing's sake, it helps to have it started at 0, 0. So 3, negative 7 is our vector, and we remember that tangent is the y value over the x value. Oops, I forgot my theta. There we go. And now in my calculator, I'm going to hit inverse tangent of 7 over 3. I never put in the negative, just put in 7 over 3. That will give me what I call swooshy, the reference angle. The reference angle here is 66.801 degrees. If you got a really tiny number, go check your calculator. Make sure your mode is in degrees mode. Now that I have that, I can see that this is in quadrant 4. I also knew it was in quadrant 4 because it was going right 3 and down 7. Right and down is quadrant 4. So in quadrant 4, we remember we take 360 and minus swooshy, the reference angle. So there's 360 minus 66.801. I bang that into the calculator and that gives me 293.199 degrees. And that's all there is to that one. Now, this angle right here is the one we measured. So when I first found swooshy, the reference angle, remember we said that was supposed to be about 60 degrees, and we had 66. So that was pretty darn close. This is an excellent estimation, and it looks like this is correct. Let's hope it is, since this is about the 50th time I've done this problem. Alright, next I've got to find the unit vector. So the unit vector just takes this vector, the vector 7, let's try that again, 3, negative 7. We're going to take that vector and we're going to shrink it down so it only has a length of 1. Well, if we go back a couple slides, we saw that the real length of this vector is the square root of 58. So in order to shrink it, I'm going to divide it by the square root of 58 to shrink it down to a magnitude of 1 unit. So I just take 1 over the magnitude and then multiply by the vector. Let's multiply this through, so this is going to be 3 over square root 58 and negative 7 over square root 58. And that's all. If you wanted to check your answer, you could use your distance formula like we did before on this, and your answer should be 1 because its distance would be 1 unit. The magnitude is 1 for any unit vector. Now on to new stuff. Today we're doing vectors and dot products. Dot products are fairly simple, and I think you're going to like these. So we're going to find the dot product of 0, 3 and 4, negative 2. These are two vectors. When you take the dot product of two vectors, it's going to give you a scalar. In other words, it's just going to give you one number, and that's it. So we're going to do 0 times 4, that's 4. Then we're going to do the y's together, 3 times negative 2, negative 6. Did I just say 0 times 4 is 4? Oh my goodness, it's so early in the morning. I meant 0. Anytime I'm awake before noon is too early right now. Alright, so 0 minus 6 is negative 6, and that is my scalar. Whew! This is hard work. 0 times 4, 0. 3 times negative 2, negative 6. Put them together, negative 6. So that's our dot product. Next, we're going to do the same thing. We're just going to put in a little extra fluff here. So there's our u, there's our v, there's our w. Those are all just given to you. They'll be different every single time we do a problem. Alright, now I'm going to put u dot v here in the parentheses, and I'm just copying this. There's nothing magical about this. Everything's just getting copied. So there's u dot v, and here's w right here to negative 5. You see I'm just copying these. Now let's do the dot product. So first I have negative 4 times negative 1. And then I have 3 times 2. Those are both positive, so I'm going to put those as pluses. And then I'm just copying my 2, negative 5 down. After this, 4 plus 6, I think you would agree, is 10. And now, like I said, the dot product is just going to be a single number. It's a scalar. So it's going to multiply this vector by a scalar of 10. I do 10 times 2, 20. 10 times negative 5, negative 50. And that, Regis, is your final answer. Now go ahead and hit pause. Let's see if you can do this one on your own. I bet you can. Alright, hopefully you are unpaused now, and we're just going to copy down all of our vectors in place of u and v. Next, I have 2 scaling this vector, so let's multiply it by a scalar of 2, which is just doubling it in size. So I've got 2 times negative 1 is negative 2, and 2 times 2 gives me the 4. There they are. Let's multiply. Negative 4 times negative 2 is positive 8. 3 times 4 is positive 12. So your answer for this is my lucky number 20. On we move. The dot product of v in itself is 12. So that's the same as v dot v, right? Super easy. Now, I have a secret to tell you. When you take the dot product of any vector and itself, that's going to give you this. That's going to be the same as the magnitude squared. So v dot v is the same as the magnitude of v all squared. This is going to come in handy for some of the problems we're doing in the future. Now, in order to solve this, all I'm going to do is to find the magnitude, I need to square root to cancel out that square. So both sides get square rooted just like that. That gives me the magnitude of v equals, now normally we would put plus or minus, but since magnitude is a distance, we're going to leave this as a plus. It's the same as the square root of 12. And of course I would love to reduce that. Remember that 12 is 4 times 3, so the square root of 4 is 2. The square root of 3 is just the square root of 3. So 2 square root of 3 is what we're looking for. Now let's move on and find the angle between 2 vector, or as we would say in America, vectors. There we go. Alright, so here are our 2 vectors, u and v, and all I'm going to do is I'm going to follow this magical formula up here. This is the angle between 2 vectors formula, and in order to do this you're going to need to use an inverse cosine. But before we get ahead of ourselves, let's just go ahead and plug these in. Instead of u, I'm going to put my 4, 2. Instead of v, I'm going to put 2, 5. Now on the bottom, I need to know the magnitudes of u and v. So let's do that over here. Magnitude of u, remember that's when you take that distance formula, which is the little square rooty thing. We're going to take 4 squared and 2 squared and add them together. Remember, normally you want to have these in parentheses, but since they're all positive, it doesn't really matter here. So this is 16, and that's 4. 16 and 4 gives me 20. And I'm just going to leave this as the square root of 20. You'll see why in a moment. Next, let's find the magnitude of v. In order to do that, again, I'm going to do the square roots. I've got 2 squared and 5 squared. That's going to give me the square root of 4 plus 25 is 29. Alright, now I have those 2, and notice they're touching each other, so that means they're going to multiply. So I have the square root of 20 times the square root of 29. Okay, not bad so far. On the top, let's take the dot product. 4 times 2 is 8. 2 times 5 is 10, so I've got 8 plus 10. That's going to give me 18. Then on the bottom, I'm going to go ahead and multiply those 2. They are both inside square roots, so I'm allowed to do that. I have 20 times 29. That's going to be 580. Finally, I need to take the inverse cosine of both sides. In order to do that, I break out my calculator, press the on key, hit second cosine, and 18 divided by the square root of 580. Depending on your calculator, if you've got the old school one, you might need to end this with a double set of parentheses. If you've got the nice new one that shows you what's under the root, then completely ignore that. Alright, so you press equals, and assuming you're still in degrees mode, which I don't know why you wouldn't be, you have the answer 41.634 degrees. Alright, then we always look back to our answer. Does that look like a 41.6 degree angle? Well, yeah, that looks pretty good. It's pretty close to a 45-degree angle, and yeah, that's about right. All right. Oh, by the way, if you would ever do this and you get a negative number up here for your scalar on top for the dot product, don't freak out. This is the one thing where you can go ahead and type in the negative number, because if it's negative, that's just going to mean that it's obtuse. It's going to still give you the right answer if you plug in a negative number, unlike those other problems that we did before. All right, orthogonal vectors. These two vectors just mean that they're perpendicular. They create perpendicular 90-degree angles. So two vectors are orthogonal when their dot products are 0. So we have to figure out, are u and v here orthogonal? All we do is take the dot product and see if it equals 0. So, does it equal 0? We'll find out. 3 times 4 is 12. Negative 2 times 6 is negative 12. Does that equal 0? Yes, it does. So you would say, oui, they are orthogonal. Now projections. It really is supposed to say projections. There we are. All right, so projections. This is going to be kind of a tricky one to think of, but I have an analogy that's going to make your life a little bit easier. So we're going to pretend that we have a set of lights like this one, except instead of just one light, it's going to be a large, long hallway full of lights at the top of the ceiling. So the ceiling is always, hopefully, parallel to the ground. So this yellow line represents just a ton of lights that are all over. Okay, so since this is the set of lights and it's shining straight down, it's going to create a shadow on the ground. And in order to figure out where the shadow goes, you just make some perpendicular lines. So that one's perpendicular to his behind. This one's perpendicular to the ground, touching the edge of his nose. And we're going to pretend that I actually measured this out, and this is really perpendicular. Okay, so his shadow is going to be this vector right here. Since he's going uphill, there we go. Since he's going uphill, it's going to point uphill. So that vector right there is going to be his shadow. This is the same as saying this vector is the projection of the old man onto the ground. All right, so once again, this vector is the projection, or the shadow, the projection of this old man onto the ground. All right, that's basically what we're going to be doing here. Now I have a bunch of steps here for you. I have a magical formula here as well, and instead of just this formula, there's actually one that I remember better. So let me show you another way to put this. So this right here says the projection of u onto v. So the tiny one is the one that you're projecting onto. And in order to figure that out, you could use this formula right here, which is great. Or another way to think of it is it's the dot product of u and v over the dot product of v and v. Remember I said that the magnitude squared was the same as the dot product with itself. So we have that times vector v, the scalar. Okay, so dot product of u and v, dot product of v and v times, or scaled by the vector v. Alright, this will make sense once we do one, I think. So we're going to find the projection of u onto v. Step 1, draw an altitude. Step 2, draw the shadow and label it. Step 3, we're just going to label this one W2. Alright, here we go. First, before we can do anything, we need to find what the vectors are. So vector v, this is ending at the point 1, 2, 3, 4, 5, 6, 7, 8, 2. So vector v is 8, 2. Vector u is 1, 2, 3, 1, 2, 3, 4. So that is 3, 4. That's u, that's v. Alright, so now we're set. We have our two vectors written down. Next, we need to do our dot product on the top. So we're going to do the projection of u onto v is, and on the bottom we're just writing v twice. So basically this whole equation here, the whole formula, is all v's except for that first thing is u. Alright, and then this is also v. So you're seeing that you're writing 8, 2 4 different times, and then that u, the 3, 4 is up at top. Alright, next let's do our dot products. On the top, that is 24 plus 8. 24 plus 8, 32. On the bottom, I have 64 plus 4 is 68. So that is my scalar. Now, it would probably make my life a little bit easier if I would reduce that fraction. So I go ahead in my calculator, I'm typing in 32 fraction, or divide by, 68, and then math, enter, enter, and it gives me the fraction 8 over 17. So this is going to make my life a little bit easier, make the numbers smaller. Let's do that. Finally, we're going to scale this to a factor of 8 over 17. So that's going to give us 8 times 8 is 64. And 2 times 8 is 16. Alright, so this would be the component form of W1, the orange vector here. Let's see if there's an easy way to check our answer. So go ahead, hit 64 divided by 17. My calculator says that this is about 3.76. And then if I did 16 divided by 17, we know that's going to be close to 0.9. It's about 0.94. Alright, now chances are I would ask you for an exact value, so I would want that one right there. But we're just doing this, we're simplifying the fractions or putting them in decimal form just to help us figure out if the answer is right. Now this says that the vector is going to the right 3.76, so 1, 2, 3.76, going to be like there, and then I'm going to go up 0.94, so up to almost 1 from there, and that would take me, there, look at that. That worked out perfectly, didn't it? Alright, so that's a quick, easy way to check your answer. On we go to work. There are a couple of formulas for the work, but here, let me do these for you so that you kind of understand what's happening. So, I've got a truck. It weighs 36,000 pounds, and it's parked on a hill that's inclined at a 10-degree angle. Now, something terrible has happened. The parking brakes have completely gone out, and you're trying to save the life of a little old lady who's at the bottom of the hill. It is totally up to you to be able to keep this truck from rolling backwards downhill. And in order to do that, we're going to have to use some trig. Now, we're going to think of this, let me zoom in here. We're going to think of the F vector, this one right here, as the force of the truck. The force of the truck, it's like the weight of the truck. So it's gravity pulling the truck down, down, down. So F, you would agree, it's going down 36,000 pounds. So if I had to put this in vector form, it's not going to the right. Gravity doesn't go to the right, except when I'm driving. And it's going to go down, so it's negative 36,000 pounds. So that's my force vector. Now we're imagining that there's a set of spotlights right here, and it is shining on my force vector, creating a shadow right here on my ramp. So the truck is wanting to roll downhill, and we're going to figure out what the magnitude of that vector is to figure out how much force we need to keep it from going downhill and squishing the old lady. Now you would agree that my theta is 10 degrees. So I'm going to write theta equals 10 degrees here. Now, sadly, I'm going to need more room, so I'm going to just do some copying and pasting. Alright, let's go back up to where I have more room. That was a total fail. Sorry about that. Alright. so there's my information. Next, I have to see what I can do to figure out this vector, what it is. So my first step is, let's go ahead and find the unit vector. So just using my direction angle, I can pretty easily figure out the unit vector. Remember that the unit vector, let's call this, well, let's call the unit vector u, that makes sense. So my unit vector, we always take the cosine of theta, I, plus the sine of theta, j, or you could think of this in component form, cosine, comma, sine. Either way, it's the same thing. So our degree, our angle is 10 degrees. So you can write it in linear combination form like above, or in component form like below. Either way, these both mean the same thing. And now all I have to do is type this in the calculator. Again, make sure you're in degrees mode because we have degrees there. This gives me the vector 0.9848 and 0.1736. Just like that. Alright, now that I have that, that is my unit vector. Now I know that's being multiplied by a scalar of how big that truck is, so I need to figure out how much force that truck is pulling back downhill. In order to do that, I'm going to use that same magical formula that I just did with the projection of the force of the truck onto my vector. This one, onto vector v. Alright, so in order to do that, I'm going to take my f vector, dot my u vector here, 9848.1736, and then on the bottom, again, I'm just using that same formula that I was using before, this one here. On the bottom, I'm going to use my 0.9848.1736 twice. 9848.1736. Okay, whew, that was a lot of work. So on my calculator, I'm going to type 0 times whatever, I know that's going to be 0, negative 36,000 times that junk, and that's going to give me 6249.6. Now on the bottom, some of you may be thinking, wait a minute, I think I know the answer to the bottom. It just makes sense. And if you're thinking that, great job. If not, that's okay, let's figure it out. So we multiply the 0.98s times each other, we multiply the 0.17s times each other, we add those two together, and it rounds to 1. How did I know that was going to be 1? Well, remember, this is going to be the magnitude squared of that vector. That vector was a unit vector, right here. So this unit vector has a magnitude of 1, and 1 squared is 1. So for my final answer, I would take all of this times my original vector that I started with, the 9848.1736. Alright, now before you go nuts and multiply through that scalar, I'll tell you, we don't even need to do that. Remember, our whole goal was to figure out how much force is going to be required to keep the truck from rolling down the hill. And the way to do that, that was a negative, sorry about that, and the way to do that is to just look at the magnitude. We already know the magnitude because this is the scalar. So our magnitude is 6,249.6. This is how much force we need to be able to have in order to keep the truck from going down the hill. It's a good thing I've been working out. Okay, on we move. Oh, believe it or not, email is on my Canvas page. And finally, if you need to, get some extra help, you can either email me or you can of course just figure out what my office hours are. They're located right there on my Canvas page as well. Give me a call or whatever. Something